All right, hi. So I am re-recording the lecture from yesterday because apparently my resolution got changed. I had hooked up a secondary monitor recently, and when I did that, it changed how OBS was recording my desktop, which is why in the previous version of this video that I uploaded yesterday night, you only saw the upper right corner. So I'm going to do everything again, and yeah, so here we go. This is the lecture for 6/19/20, and I will be talking about vector spaces today. So, in order to motivate vector spaces, I want to return to kind of a more elementary notion, something that you probably have all seen before. So let's think about functions. F from A to B. So here, F is said to be A is said to be the domain, and B is said to be the codomain. And a function is a rule that assigns to every element of A a unique element of B. In linear algebra, we are concerned with special kinds of functions. So and these special kind of functions, we call them linear. Now, here's the thing about linear functions, is that linear functions, when we actually do get around to formally defining them, they depend on A and B here having a little bit of extra structure. And what we kind of want to make clear at this point is what this extra structure is. And one way to understand it is to kind of look at a very, very good motivating example, namely the setting R2. So you've all seen R2 before. This is the Cartesian plane. And you've all probably seen vectors in R2 before. So a vector is, of course, you have an arrow that goes to a point AB, and you denote your vector like this. And I'm going to denote it as a column vector. So A in the first component, B in the second component. So we think of vectors as arrows in the sense that they have a direction and a magnitude, and they always begin emanating from the origin. Now, the cool thing about vectors is that unlike just points, vectors actually have a little algebraic structure to them. So for example, if we have a second vector, say with components C and D, as pictured, then we can add this vector with this vector. And basically the way that works is you go along this path, and then you go up this path. And this creates a parallelogram. And regardless of whether you go this way and this way, or this way or this way, you get to the same point. And so we look at the vector that starts at the origin and then goes all the way to that point. And this vector right here is going to be the sum of the orange vector and the red vector. So here the orange vector has components CD, and the blue vector will have components A plus C and B plus D. So that is how vector addition works. Now, vectors also have another property, namely scalar multiplication. So here's how that works. Suppose you have a vector. It starts from the origin. Maybe it goes over to a B. And you have a scalar. Say you have the number 3. Then you can take the number 3 and you can multiply it by the vector. And this simply results in multiplying each of the components by 3. So we get 3a, 3b. And what this does is it essentially scales this vector by a factor of 3. So we get this vector. It points in the same direction, but it has 3 times the length. So these two operations, vector addition and scalar multiplication, endow R2 with something that is known as the structure of a vector space. It is very useful to kind of take this structure and formally analyze it. The reason being is that it appears over and over again in different contexts in mathematics. So, for example, the techniques of studying vector-like structures can equally be applied to, say, the study of continuous functions, as we'll see, as it can be to the study of R2. And this means that the techniques of linear algebra can be applied to things far more complicated than simply just, maps from Rn to Rm. But we shall see this. So, the first bit of business we want to do is we want to abstract the structure that we've seen here, the vector addition and the scalar multiplication. So let me give you guys the definition. So a vector space is an object V, a set, that is characterized by having two operations, an addition operation, and a scalar multiplication operation. And these two operations are expected to satisfy certain compatibility properties. So for example, when you add two vectors together, the ordering in which you add them should not matter. When you add 3 vectors together, vector addition should be associative. So it shouldn't depend on which way you kind of put your parentheses in. There should exist a 0 vector such that if you add it to any other vector, you get your vector back. For every vector x and v, there should exist a negative x and v, such that if you add the negative to your vector, you get 0. If you take the vector sum of x plus y and you multiply it by alpha, then the alpha should distribute over the addition to get alpha x plus alpha y for each scalar's alpha and any x and y in v. And if you look at alpha beta times x, then it should distribute over that. Likewise, it shouldn't matter if you multiply alpha beta and then apply it to x, or if you apply a beta at x and then you multiply by alpha. And finally, if you multiply any x by the scalar 1, you should just get x back. So this is an abstraction of properties that we already have in R2. But why don't we verify some of these for R2? So let's verify some of these for R2. So you guys can see that A1 here, the fact that addition is commutative, essentially corresponds to this picture, where these two vectors can be made into a parallelogram. And that's what we mean when we say ordering of addition doesn't matter. So that picture actually kind of gives you a proof of A1 in the case of R2. Now I won't prove A2 because you can do that if you want, it's very easy. I will prove A3 because it's also easy, but I just kind of want to show you some of the tedious aspects involved in verifying vector space structure. So what we can do is we can take our 0 vector to simply be the vector with entries 0, 0. 0 in the first component, 0 in the second component. Now, if we add this vector to any other vector, well, of course, we're going to get the other vector back. So AB plus 0 and 0 is just going to give me an A and a B. And so that verifies A3. Now that we have our distinguished 0 element, A4 asks for any vector x in V, there exists a negative vector such that if you add your vector to the negative vector, you get 0. So let's verify that as well. So we look at AB, and then we add to it negative A, negative B, and this gives us 0, 0, which is our distinguished 0 vector. So it's also true that for every x in our vector space, we have a corresponding negative vector. I'll also check A7. So let's suppose we have a vector AB, and we multiply it by C, and then we multiply the resulting vector by D. Well, this is going to be the same as D applied to CA, CB, which is the same as DCA, DCB, which is the same as DC, AB. So this calculation we just did right here verifies A7. And I don't have to write it down, but you can easily see that if you multiply any vector in R2 by 1, you simply get your vector back. So all these axioms are always very, very straightforward to verify. They don't generally require much work. So taken together, they characterize the notion of an object called a vector space. So let's look at some examples. Let's start with the canonical example that generalizes the one we already looked at, Rn. So Rn will be the set of column vectors A1, A2, AN, where the AIs are real numbers. So you can verify, and the proofs are virtually identical to what the proofs are in R2, that this is also a vector space. So let's just look at a specific example that'll be relevant to us later when we're talking about examples. We can also look at R3. R3, we can visualize it like this. So we draw the coordinate axes like this. This is x, this is y. And we can draw vectors in here. So here, say this is A, this is B, and this is C. Then this vector right here is the vector A, B, C. And you can check that the parallelogram law for addition that we exhibited in R2 also holds in R3. And that's the first thing that you have to check to verify axiom A1 for R3. But really, all the axiom verifications are very, very simple and straightforward, so I will admit them. So these give us some examples of vector spaces, and in many ways they will be our favorite examples for the rest of the course. But one point I want to emphasize is that there's many, many other examples. And they're kind of a little less intuitive and natural. So here's one. We're going to look at the set of continuous functions on an interval AB. So this will be continuous functions f from the interval AB to the real numbers. So this turns out to be a vector space. So that's my claim. Now, I haven't defined a notion of dimension yet, but at least morally, you would think R2 is two-dimensional. You would think R3 is three-dimensional, and you would think Rn is n-dimensional. And if this CAB turns out to be a vector space, you might think that it also has a dimension, and it does, and it turns out to be infinite dimensional, because there's lots of continuous functions. So as a vector space, this is in some sense much bigger than any of the examples that I just talked about. But it still is a vector space, which means the techniques of linear algebra can still be applied to it. So to verify that, let's see how the axioms apply. Oops, so let me go over here, take this. So in order to show that this is a vector space, what we need is an addition operation, and we need a scalar multiplication operation. And then we need to check that axioms A1 through A8 are satisfied. So here's how the addition operation works. Suppose we have two functions f and g that are in this set, so C of AB. Then we can define f plus g of x to be equal to f of x plus g of x. And as you'll recall from calculus, whenever you take the sum of two continuous functions, you get a continuous function. So this addition operation takes two inputs, and it produces another output that also lives in this set. So it's very easy to define addition. Let's define scalar multiplication. So alpha will be a real number, and f will be an element of the continuous functions from AB into the real numbers. And we can define the scalar product of alpha and f to be the function that evaluates to simply alpha times f of x. So this gives us an addition operation and a scalar multiplication operation. And the claim is that under these two operations, axioms 1 through 8 are satisfied. So let's go through some of them. How about we check axiom A1? So A1 verification. So we want to check that addition is commutative. So let's consider the sum of f plus g evaluated at x. Well, this of course is by definition f of x plus g of x. But now this is a real number and this is a real number, and addition of real numbers commutes, so this is the same thing as g of x plus f of x, which is the same thing as the sum of the functions g plus f of x. So this verifies commutativity of addition. Next, why don't we verify axiom A4? So A4 verification. So for any x in our vector space, there should exist a negative x in V, such that if you add them together, you get 0. So how about we first say what our 0 is? So our 0 is going to be the continuous function that's just equal to 0 everywhere. Now, if we add 0 plus f to any continuous function f, then this is the same thing as 0 of x plus f of x. But 0 of x is just 0. And when you add 0 to any real number, you just get your real number back. So this shows that 0 plus f of x is equal to f of x. So that verifies A3. Now let's do A4, which is the one we actually want to do. Why don't we set negative f of x to simply be negative 1 times f of x. Now, look what happens when we add f of x to, or when we add f to negative f. Well, we're going to get f of x plus negative 1 times f of x, which is just going to be equal to 0, and this is the 0 function. So this verifies A4. So we've now verified A1, A3, and A4. And if you wish, you can go through this list and you can verify the remaining axioms, and you can see that they're all true for this set. So CAB is a vector space. Let's do another example. Suppose we look at the following differential equation. So we're going to consider y double prime of x plus y of x equals 0. Now, I'm hoping that most of you have seen differential equations before. If you haven't, what you need to understand here is that there are techniques that you can use to solve such an equation. They're not hard. And if you solve such an equation, you find that the set of solutions is going to be the following set. Alpha times cosine of x plus beta times sine of x, where alpha and beta are real numbers. So this set of solutions is a vector space. For example, if you set f of x to be equal to alpha times cosine of x plus beta times sine of x, and you set g of x to be equal to, how about c times cosine of x plus d times sine of x. These are both solutions to this ODE, but if you add them together, then their sum is the same as alpha plus c times cosine of x plus beta plus d times sine of x. And so this is also a function of this form. So whenever you take two functions in the set of solutions and you add them together, you get another function in the set of solutions. So you can likewise check that if you multiply something of this form by a scalar, you get another thing of this form. So it's closed under scalar multiplication as well. So the set of solutions here forms a vector space. Let's do another example. How about we look at R of x? So R adjoined x is the set of single variable polynomials p naught plus p1 times x plus p2 times x squared plus blah, 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 all the way up to pn times xn, or times x to the n for some n. So for example, 5 is an element of this set, but so is 5 plus x squared, or 10 plus 3x plus 6x cubed. These are all elements of this set, because this set contains all polynomials in the variable x with real coefficients. So here's the claim. Rx is a vector space. So what we want to do is we want to verify this. And the verification process will essentially go the same way that it went in previous examples. We'll choose some axioms to look at and we'll verify those specifically, and I'll leave the rest to you as an exercise to verify if you are bored. So, before we can even verify any axioms, we should at least say what the addition and multiplication operations are. So, what I'm going to do here is I'm going to write p of x for the polynomial that is p naught plus p1 times x plus p2 times x squared plus blah, 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 blah. And I'm going to write q of x for the polynomial that starts with q naught plus q1 times x plus q2 times x squared plus blah, 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 blah. Now, I can add them together. And the way I add them together is the polynomial sum, p plus q of x, is obtained by summing the coefficients. So the zeroth coefficient is going to be p naught plus q naught. And then the coefficient of x is going to be p1 plus q1 times x plus p2 plus q2 times x squared plus blah, 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 blah. And then we can also define scalar multiplication. So if alpha is a real number, then alpha times a polynomial p is just going to be what we get when we multiply every coefficient of p by alpha. So the 0 will have p0 times alpha plus alpha times p1 times x plus alpha times p2 x squared plus blah, blah, blah. So I have an addition operation and I have a scalar multiplication operation. And it remains to verify that all the axioms of a vector space are satisfied. So let's choose one to focus on here. How about I do A2? Because I haven't verified an A2 axiom yet. So let's go back here and let's copy my two vectors, or my two polynomials. And I'm going to add a third one, and this will be r of x, and it will have coefficient r naught plus r1x plus r2x squared plus blah, 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 blah. Now, if we evaluate p plus q plus r of x, you can check by calculation that the thing you get is you're going to have P naught plus R naught, or plus Q naught plus R naught, and then plus P1 plus Q1 plus R1 times X, and then plus P2 plus Q2 plus R2 times X squared plus blah, 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 blah. And this is what you get just by computing this, but this is exactly the same thing you get when you compute P plus Q first, and then add to it R. So, via this explicit calculation, you're able to verify that axiom A2 holds. You can also verify, for example, axiom A4 by noting that the zero polynomial is just 0. And we can define the negative of a polynomial to be simply the polynomial where all the coefficients are negated. So we have negative P naught minus P1 times X minus P2 times X squared plus blah, 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 blah. And you can check that if you add negative P to P, you simply get the zero polynomial. And so this verifies A4. So for any given vector space, you have to verify all of these different axioms. But once they're verified, you know that you actually have a concrete vector space in your hands. So the last example I'm going to give you guys for now is the set of matrices. So this is R, and then up here we put N, and we read this N by M. So this is going to be the set of all N by M real matrices. So, claim R n by M is a vector space. So I'm not going to verify any of the axioms for this because they're all really easy, but I will just say explicitly what the operations are. At least I'll do it in a concrete example, say R2. So, or R2 by 2. So let's suppose one of our matrix is A, B, C, D. Call this A. And let's say our other matrix is B, and this is X, Y, Z, W. Then we can form their sum. And we're going to get the matrix that we obtain simply by adding component by component. So we have A plus X, B plus Y, C plus Z, and D plus W. And so this gives us our addition operation. And then we have a scalar multiplication operation as well. So let's suppose we have a real alpha, and we multiply our matrix A by alpha. What we get is we get the matrix alpha A, alpha B, alpha C, and alpha D. So this is how scalar multiplication is defined. And you can see, or rather you can verify, that for this operation and this operation, all the axioms of a vector space are true. So now we have a good deal of examples to play with. So I want to introduce another notion, and this notion is best understood by example. Let's look at R2. So this is the set of all vectors in the Cartesian plane. And let's look at a particular subset of it. So say S in R2. And S is going to be the set of vectors of the form A, B, where A is equal to negative B. So for example, one such element of this vector space is the vector 5, -5. Another such element of S is the element -7, +7. And now I want to make the following observation. Say I take these two elements right here and I add them together. Well, if I add them together as vectors, 5, -5 plus -7, 7. Then what I'm going to get is -2 up here, +2 down here. But this is a vector that is also in the set. In fact, in general, if we have alpha, or we have A, -A, and we add it to B, -B, then what we get is A plus B in the first component, -A plus B in the second component. And this shows that whenever you have two vectors in this subset and you add them together, you get yet another element of the subset. So we say that S is closed under addition. But moreover, we can make another observation. Suppose I take a vector in S, so maybe my vector is alpha, -alpha, and I multiply it by a scalar, say beta. Then this is the same thing as alpha times beta minus alpha times beta. So if you take any vector in S and you multiply it by a scalar, you get back another vector in S. So S is closed under scalar multiplication. Okay. Now, why don't we try to understand what S actually looks like? If we draw a picture, then we can visualize S as follows. Well, if it's the set of vectors AB where the first component is negative the second component, it's precisely going to be vectors like this. Or like this. Basically vectors that lie on the line y equals -x. In fact, this is precisely the set of vectors on this line. And if you take any two vectors on this line, what we've verified is that once you add them together, you get yet another blue vector, or you get yet another vector on this blue line. Likewise, if you take any vector on this line and you scalar multiply it, you get yet another vector on this line. So S sits inside R2, but it is also a vector space in its own right. So we're going to formalize this notion with the concept of a subspace. So if S is a non-empty subset of a vector space V, and S satisfies the condition that alpha x is an element of S whenever x is in S for any scalar alpha, and whenever you have two elements of S and you add them together, you get yet another element of S, then S is a subspace of V. And here's the fact. every subspace is also a vector space. So we've already exhibited one example of a, oops, let me close that and go back over here. We've already exhibited one example of a subspace. I want to give you guys some more examples. So let's go up to R3. And I'm going to give you two different examples in R3. So first let's visualize it. R3 kind of looks like this. I'm going to draw a second picture. And I'm going to define two subsets of R3. My first subset is going to be the set of vectors of the form A, B, C, where C is equal to 0. And my second set, S prime, is going to be the set of vectors A, B, C, where not only is C equal to 0, but B is also equal to 0. So let's look at the first set. These are precisely vectors that have no z component, if this is x, y, z, which means the vectors in S are precisely vectors that lie on the xy plane. So we can visualize S as the xy plane, like this. This is S. Now, we can also visualize S prime. This is the set of vectors where both B and C are 0. So these vectors can only point in the x direction. So as a subspace, this is precisely the set of vectors that lie along the x-axis. So even though S and S prime are both subspaces, note how different they look. Again, I haven't defined dimension, but morally, S is two-dimensional. And again, morally, S prime is one-dimensional. So we have S and we have S prime. This is to kind of illustrate a phenomena that you can have subspaces of different sizes, and some subspaces are bigger or smaller than the others. For example, in this picture right here, S is a subspace of R3, and morally a two-dimensional one. But S prime is actually a subspace of both of them. So it lives inside S, but it also lives inside R3. So this kind of indicates that subspaces can be big or small, and in some sense how big they are or how small they are corresponds to the number of equations you impose. Again, I'm not being rigorous, but when you apply one constraint, like c equals 0, it's almost like you're cutting down the ambient dimension of R3 by 1. And then when you apply two equations, it's almost like you're cutting down the ambient dimension of R3 by 2. And in time, I will make that statement rigorous, but for now, we're going to have to do a bit more definitions. Anyways, now that we've looked at some concrete things, let's look at something that's a little less concrete and actually verify that it's a subspace. So I'm going to look at S in our 2 by 2. So this is going to be a set of 2 by 2 matrices. And it's going to be the set of matrices A, B, C, D, where A plus D is equal to 0. And so the claim is that S is a subspace. So I'm going to choose 2 matrices in S. Say A is equal to A, B, C, D, where of course I'm going to have AD is equal to 0. And then I'm going to choose another matrix B, and this will be equal to X, Y, ZW, where X plus W is equal to 0. Well, this will also be an element of X, or S. And now I'm going to consider what happens when I add them together. So I look at A plus B. Well, this will be the matrix A plus X, B plus Y, C plus Z, and D plus W. And what I have to verify is that after adding these 2 matrices together, this condition still holds. So I have to check that A plus X plus D plus W is equal to 0. Well, this is the same thing as A plus D plus X plus W. And this right here is 0, and this right here is 0. So when you add them together, you just get 0. So this is also an element of S. That shows that it's closed under addition. Now, we also have to check that it's closed under scalar multiplication. So for example, if I take this A over here, and I multiply it by a scalar alpha and the real numbers, then alpha times A is the matrix A alpha, B alpha, C alpha, and D alpha. And I have to check that A alpha plus D alpha is equal to 0. But notice that I can just factor out the alpha, and so this is the same thing as alpha times A plus D. And going back over here, we see that A plus D is equal to 0, so alpha times A plus D is also equal to 0. So we verified that as a subset, this is closed under addition, and closed under scalar multiplication, and thus it has to be a subspace. Now, I want to modify this example a little bit to kind of show a little bit about what can go wrong. Suppose I went back to this condition right here, and I modified it. So I get rid of the 0, and I replace it with a 1. And now I claim that S is not a subspace. Because here we have A plus D is equal to 1, and we have X plus W is equal to 1. But now look what happens when we add these 2 together. Well, this is 1, and this right here is now 1. And so their sum is 2. Which means that when you add A and B together, and these are both elements of S, the sum is not an element of S, so it's not closed under addition. It's also not closed under scalar multiplication, because, again, if A plus D is 1, and you multiply alpha by A plus D, what do you get? You get alpha. And unless alpha itself is 1, you're not going to get something that lives in S. So S is not a subspace. So when you're looking to see if something is a subspace or not, you have to pay very, very close attention to the condition that defines it. Because if that condition fails to be true, a lot of things can go wrong. All right, so let's do an even more sophisticated example. So let's recall the set of continuous functions. Okay, so what do we do here? This is the set of continuous functions, a, b to r. Well, we're going to define a subset of this. C1 AB is going to be the set of continuous functions from A, B to R, satisfying the following properties. F is differentiable. And F prime is continuous. And so, first off, note that as a set, this Y is inside the set CAB. And I don't know if I've used this notation right here before, but this means subset. This is red subset. And so given that this is a subset of this, we want to know if it is a subspace. Well, it turns out that it is a subspace. So the reason it's a subspace is that the sum of two differentiable functions is differentiable. So if I take two elements in the set, I add them together, I get another differentiable function. And the sum of the derivative of the sum is the sum of the derivatives. So this tells us that if I take two functions f and g and I add them together and they live in here, well, first off, f plus g is going to be differentiable, and the derivative of f plus g is simply going to be the sum of the derivatives. And because this is continuous and this is continuous, when you add two continuous functions together, you get another continuous function. So this C1 of AB actually turns out to be a subspace. The only other thing you have to verify is that if you multiply any function in here by a scalar, these two properties still hold. But that's easy to see. When you multiply any differentiable function by a scalar, it stays differentiable. And the derivative of a function times a scalar is simply the scalar times its derivative. So if the derivative is continuous, so will the scalar times the derivative. So we're able to conclude from this that C1 of AB is actually a subspace. Now let's do a more interesting example. Let's go back up here and let's look at our differential equation. So recall that we analyzed the solution set of this, and we showed that the solution set was a vector space. In fact, this was the solution set right here, so I'll pull it forward. Well, here's the claim. Actually, before I say it, I should say one thing. Whenever you're studying differential equations like this, one thing that you're often interested in is you're interested in posing initial conditions. Initial conditions essentially describe what kind of solution you're looking for. So, for example, an initial condition for us might be y of, let's see, y of 0 is equal to 0. Or actually, how about this? Y of pi over 4 is equal to 0. So what I'm doing is looking at solutions to this differential equation, but I'm imposing the condition that when you evaluate at pi over 4, you get 0. So for such a function, f of x equals alpha times cosine of x plus beta times sine of x. If we evaluate this at pi over 4, then we get f of pi over 4 is going to be equal to alpha times the square root of 2 over 2 plus beta times the square root of 2 over 2. And we're requiring that this is equal to 0. And so this implies that alpha plus beta is equal to 0. So this initial condition corresponds to the set of solutions alpha times cosine of x plus beta times sine of x where alpha and beta are real numbers and alpha plus beta is equal to 0. And so this gives us a set S. S lives inside our set of solutions. And it turns out to be a subspace. Morally, this right here is a two-dimensional subspace. Or this is a two-dimensional vector space. And S right here is a one-dimensional subspace. So we can see how in problems arising from the theory of ODEs, imposing initial conditions actually just corresponds to sometimes the selection of subspaces. Okay, so let's consider yet another example. I want to look at null spaces. So an n by m matrix determines a function say we denote our matrix by A from the set of n-dimensional column vectors to the set of n-dimensional or m-dimensional row vectors given by what you do is you take a vector v in Rn and you map it to A times V. So we can now associate to this A a subspace of Rn. So the null space and I'm going to call my n by m matrix A, which is going to be the same label I use for the function, but that hopefully shouldn't cause any confusion. So the null space of a matrix A is the set of vectors in Rn, or I'll say the set of vectors V in Rn with A times V is equal to 0. So let's do some examples. I'm going to consider the following matrix. So A is going to be this matrix. And we can think of it as a function from R4 to R2, because it's a 2x4 matrix. Now, we want to figure out what vectors in A go to 0. So this amounts to looking at the following linear system. 1, 2, 1, 1, 1, 0, 0, 1, and then maybe I'll give myself some space here. Times a vector x0, x1, x2, x3. And we want this to be equal to 0, 0. Now what we're going to do is we're going to apply row operations to simplify our life. So if we apply, actually, do I want to do that? I don't even really need to do that. No, I don't need to do that. So if we look at this equation, what we're interested in is we're interested in x0, x1, x2, x3 that satisfy this, which means we want x0 plus x1 plus x2 to be equal to 0. And we want 2 x0 plus x1 plus x3 to be equal to 0. So let's give some examples of vectors that satisfy these two equations. So one example is the vector, let's see, what's a good one? How about the vector 1, and then I'll have a -2 in the last component, and a -1 here. Now, you'll note that if we take 1 plus 0 plus -1, this corresponds to the first equation here, we get 0. So, this is a vector that's going to be in the null space. And this will also satisfy 2 times 1 plus 0 plus -2 is equal to 0, corresponding to this equation. So since it satisfies both of these equations, it does in fact lie in the null space. Now, the one thing I want to say about the null space is that the null space is actually a subspace. Here's how we can see this. Suppose V and W are both in the null space of A. Well, what this means is that A times V is equal to 0, and A times W is equal to 0. But these together imply that A times V plus W is equal to 0. And likewise, if alpha is a real number, then alpha times V, if we apply A to it, this is the same thing as alpha times A times V, which is the same thing as alpha times the 0 vector, which is just the 0 vector. So the null space is closed under addition, and it's closed under scalar multiplication, so it's actually a subspace. All right. So now we have a good deal of examples at hand. So I want to introduce another definition. So this is going to be the notion of linear combinations and spans. So suppose we have a vector space V, and we have n vectors in it. Then a sum of the form alpha 1 v1 plus alpha 2 v2 plus blah 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 alpha n vn, where alpha 1 through alpha n are scalars, is called a linear combination of v1 through vn. The set of all linear combinations is called the span of v1 through vn. And we denote the span by this notation. So the span is yet another way that we can construct subspaces. So I actually have to verify that for you. And so here's my claim. Span of v1 through vn is a subspace. All right. So let's look at alpha 1, or let's look at two elements of the span. So I'm going to look at an element V and an element W. And so V here is going to be alpha 1 V1 plus alpha 2 V2 plus blah 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 alpha n Vn. W here is going to be beta 1 V1 plus beta 2 V2 plus blah 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 beta n Vn. And now let's consider what happens when we add these two together. We get V plus W. And this is going to be alpha 1 plus beta 1 times V1 plus alpha 2 plus beta 2 times V2 plus blah 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 alpha n plus beta n Vn. So you'll note that when we add this vector to this vector and we get this, this is also in this form, which means that the sum of two vectors in the span is also an element of the span. Likewise, if we have an alpha that's a real number, and we multiply, actually let me choose a different letter here, say gamma. So say I have a gamma here, and I multiply my vector v by gamma, then I see that gamma times v is going to be gamma alpha 1 times v1 plus gamma alpha 2 times v2 plus blah 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 gamma alpha n times vn. And likewise, this is also an element of this form. It's a linear combination, which means it lies inside the span of v1 through vn. So this is the notion of span. And span gives us yet another way to construct subspaces. So now I want to give you guys another definition. This is the notion of a spanning set. So the set V1 through Vn is a spanning set for V if and only if every vector in V can be written as a linear combination, V1, V2 through Vn. So, for example, let's consider the following set. E1 here is going to be the vector 1, 0, 0. E2 is going to be the vector 0, 1, 0. E3 is going to be the vector 0, 0, 1. So we have these three vectors. And what I want to do is I want to show that the span of E1, E2, E3 will be equal to R3. So here's how I'll show that. First off, note that this is precisely things of the form, or linear combinations. AE1 plus BE2 plus CE3, where A, B, and C are real numbers. And this is the same thing as the set of vectors A, B, C, where A, B, and C are real numbers. But every vector in R3 can be found in the set simply by choosing the components A, B, C appropriately, so this is just R3. So we're able to see that if you have these three vectors, you can express every other vector in R3 in terms of them. That's why we call it a spanning set. So now let's ask some questions. Suppose we look at the following four sets, and we want to ask which of them are spanning sets. Well, I claim that A is a spanning set because we already know that every vector in R3 can be written in terms of E1, E2, E3 by our calculation right here. So that's easy. So how about we look at B and we ask, is this a spanning set? Well, basically what we want to do here is we want to understand which vectors, B0, B1, and B2, can be written as a combination of A, 1 times 1, or 1, 1, 1, plus B, 1, 1, 0, plus C, 1, 0, 0. We want to know which vectors B0, B1, B2 are accessible. And this will be a spanning set for R3 precisely when we can write any vector for any choice of B here can be written in terms of choices A, B, C here. So we can package this all up into a matrix equation. And so it's going to be this matrix equation. And so here I have A, B, C here, and I have B0, B1, B2 here. And I want to know if I can, actually I'm going to rename these variables just to satisfy my own OCD. This will be x0, x1, x2, and this will be x0, x1, x2. And we want to know that for any choice of x0, x1, x2, we can write it as a combination of these three vectors for appropriate choices A, B, C. This corresponds exactly to this matrix equation where this is A, we'll call this vector here y, and this is x. So we want to know if A, y equals x is solvable. So this is solvable in general, and by in general I mean for any x, if and only if the determinant of A is not equal to 0. So this is just using results we proved last week. And it effectively allows us to approach this problem by doing this computation. So let's compute the determinant of this matrix. So let's set A here. And I'm going to compute the determinant of A, and I can compute the determinant of A basically via a cofactor expansion. So 1 times this the cofactor corresponding to this submatrix, and then minus 1 times the cofactor corresponding to this and this, and then plus 1 times the cofactor corresponding to this submatrix. This is going to be 1 times 0, this is going to be minus 1 times 0, and this is going to be plus 1 times negative 1, so negative 1. So this determinant is non-zero, which tells us that this system is solvable, which tells us that every vector for any choice of x0, x1, x2 can be written as a linear combination of these three vectors. So this, in fact, is also a spanning set. All right. So now let us look at C. So what we're interested in is we're interested in A times the vector 1, 0, 1 plus B times the vector 0, 1, 0. And we want to know, can any vector x0, x1, x2 be expressed as a combination of this vector and this vector? And the answer is no, because this is equal to A, B, A, which means the first component here and the second component here are the same. So, for example, the vector 1, 2, 3 is not in the span of these two vectors. So whereas A here was a spanning set and B was a spanning set, C is definitely not a spanning set. In fact, this only spans something that is two-dimensional. So now we arrive at D, and this will be the last one we do. We want to understand if this is a spanning set for R3, which means for any choice of x0, x1, x2, we can write this as a combination of A, 1, 2, 4, plus B, 2, 1, 3, plus C, 4, negative 1, 1. As before, we can convert this into a matrix equation. And if we convert it into a matrix equation, then we have A times X, or times Y, is equal to X. And the solvability of this matrix equation corresponds to whether the determinant here is not zero. So solvable in general if and only if the determinant of A is not equal to 0. And the determinant of A here is going to be equal to 1 times the cofactor plus or minus 2 times this cofactor, and then plus 4 times this cofactor. This right here ends up being 1 times 4, minus 2 times 6, plus 4 times 2, And if you evaluate this out, you get 0. Which means that this linear system is not solvable in general. Which means there are vectors with components x0, x1, x2 that cannot be expressed as a linear combination of these 3 vectors. So this is not a spanning set. This is not a spanning set. But this and this are. So that completes what I wanted to say today. So I hope you guys have a nice rest of your weekend. Let me upload this right now.